So, this thing is really at an inconvenient height. So they should have put it onto this thing.
Yeah. Can you like pull it up by the bottom of the
I think it's set up.
monitor? Yeah, the screen. Like
Yeah, but that doesn't help because the keyboard's like here.
Oh,
Doesn't exactly, it kind of helps a little. Except it's like right in your face and it's better here.
Convenient either way.
Yeah, it's like no one ever, it's one of those things, no one ever tried it, you know, they just, yeah. Let's see, so I want to, there's a couple slides in here. Yeah. Pretzel cell. That's the one, like that one. Just download it. Wait, yeah. Oops. That's good. And the pretzel cell, I guess this is the one. Like, yeah, it's 500, but I don't go that far in this. There are like 552 slides.
Oh my gosh, yeah. It opened PowerPoint.
It's pretty crazy.
That's from the first day when I was pulled up and I saw 552 slides.
Yeah. I mean, I go through a lot of them, but not all of them. I went to kind of zip through this. This used to take like a whole week. Now it's just like I zip through it. So something's out, I guess.
Just narrowed it down to important information, just so you won't get out.
Yeah, I guess I gave this a class on this in Ethiopia. They liked it, but I made a new set of notes, you know, that were kind of more coherent. So all right, so what do I want to say here? I guess I just wanted to say, oh, let me pull this thing up and project it. Okay. All right. So yeah, we're kind of looking at semiconductors have a small, so there's a band, a conduction band and the valence band. And there's this Fermi level where the electrons are in this semiconductor. And then kind of the sunlight comes in and is kind of knock the Fermi level electrons up into the conduction band, then they can leave, like they're mobile then. Right. So when it happens, I mean, it creates a hole, like the electron leaves behind a positive hole where it was before. And those holes, so the next electron over in the silicon crystal can like pop the electron in there so the hole can move over an atom. And it can do that again. So the holes can be like a positive conducting mechanism, popping like through the crystal, or the electrons can also conduct through the conduction band, like in a normal like copper or something. Right. So there's like two mechanisms. It turns out like those, depending on the material, those two can be equal. Like you'd think that the holes would be much harder for the holes to move around, but it turns out those two mechanisms can be equal, or the holes can be the dominant mechanism. The electrons can be the minor transport mechanism, depending on which material it is. Like how much the electrons are attracted into the material, I guess, or how much they're trapped. I don't know why, actually, but basically you can have either one. So then what? So basically electrons up there, the holes down here, it's negative and positive. They want to recombine. Like they want to just go back and they would just generate heat and it disappear. I mean, it would just go back to normal. So basically there's a lifetime of the electron after it gets excited. And during that lifetime, that electron has to meet this p-n junction where you have a positive, negative, and then the positive side, on the positive side, let's see, the positive side builds up electrons near the negative side, I think. I guess the positive side must build up holes near the negative side. The electrons must pile up on the negative side of the p-n junction. And then basically that leads to like a barrier for an electron to pop through. So the electron wants to pop through to the positive. So if you generate from the negative, it'll pop into the positive. And then it kind of gets trapped there because it can't go back in because it sees a wall of negative. So it's kind of stuck there for a while. It can pop back, but basically it's stuck there for a while. And that's your opportunity if there's a voltage, that's your opportunity to build up a voltage that the thing will conduct out through a circuit, an external circuit. So there's a lifetime involved in the electrons doing this operation. Anyway, so it's kind of simple and it kind of can get complicated, right? So what's going on with this thing? But anyway, the temperature, so if it's an intrinsic semiconductor, because the temperature will generate these electrons hopping, then the higher the temperature, the more the conduction, which is the opposite of copper. Like copper, the higher the temperature, the more they have lateral motion, so you get more loss, then you get less conduction, you get to higher temperature, which is kind of what you'd expect, I guess. And then with these, it gets higher conduction because you're generating the electrons. But if you dope with phosphorus or boron, then you can, with silicon, then you don't get that temperature dependence at all, and then you just have a flat extrinsic conduction. So it's a flat, non-temperature dependent conduction until you reach some temperature where intrinsic takes over. Intrinsic means that the electrons pop out because they're excited by temperature to get into the conduction band. So that's kind of the scheme of how these things work. And I went
With
through.
it going from the negative to the positive, is it the way it goes back? Is it just the attraction so strong it's able to overcome that hole? Or I guess how does that work? How does it eventually go back to that negative side?
I mean, I think they call it diffusion, you know. So, I mean,
Just through diffusion? Okay.
yeah,
I
it's
didn't know
diffusion, but there's a bias to it. Like that charge makes a bias, so it can't exactly get back very easily.
Okay.
So, but it's like rolling the dice, but the dice are a little bit weighted. So it's
Gotcha.
weighted by that bias, but they can still get enough energy to hop over the bias and get back to the hole that it wanted to go to.
Okay, gotcha.
But while it's trapped at the top, then it can make current. Then you can get current out of it. So,
Okay.
so that's kind of how they, more or less how they work. I mean, and then these VI charts are kind of what people look at. So if you have it just sitting there, so you put a voltage on it and you get a current, and this I times V is the power that you put into it. And then if I and V are negative, you get reverse bias, and then you get across a PN junction, then you get this kind of leakage current through it. So basically, the electrons don't want to flow in one way, but they'll flow in the other. It's a diode, so it only has current going in one way because of that buildup of electrons. But there's some that leak through, like that's the leakage amount. So you put a voltage on it, and you still get a little bit of current going backwards, but that still consumes energy. Like negative V and negative I multiply to give you power, right? And then positive V times I give you a power. So you're putting power into it to get the current to flow. Right? So there's a net power loss in both directions. But once you put the sunlight onto it, then this thing shifts down. Then you get positive V and negative I, and that means it's negative power. I mean, you generate power there. So this quadrant and that quadrant consume power. This quadrant generates power, and then this side is consuming power, but it's linear, so you get a linear dependence on the light. So you can measure the amount of light there. So that's a photodiode, like where you can measure how much light, quantify it by the current that goes through. And this side you just generate power. It's not a linear relationship, it's going to be this curve thing. So this is the area of interest for photovoltaics. It's like when the sunlight's on, how do you fill that gap? Usually they flip this thing around so it isn't upside down, but basically that's the fill factor. It's like how much, what that point is, what that area is, what this area is. This is if you have open current, so there's no connection through it, and then it can build up the highest voltage that it can get. And then if you have a short circuit, so you just run a wire across it, then that's no voltage, but you get the maximum current going through it. And in between is kind of your operating, where you have a drain on it, you're draining power out of it in this part, right? This part's making power. This has no power because VI, I is 0. This part has no power because V is 0. And in here you make power, different kind of rates of power production. So that's kind of how you map out. So this VI plot is kind of what you want to look at for any kind of alternative solar cell. It's also going to be the same plot. Anyway, so yeah, I mean, I usually say like transistor, but it's not. So anyway, like if you can put so you can have a PN junction and another PN junction, and then you can put a bias into the middle of this. So the current that flows through here and the voltage of that pile up electrons is really small, right? So basically, if you put a really small signal in here that changes the voltage there, so you can control it externally, then you can turn it from being it won't let current go through to letting current go through freely, right? So just by putting a small signal here, you can control a big signal here. So say you have a big power supply here, and this hooks up to a speaker, and then this is a microphone, which has almost no voltage, right? So you just feed that microphone into that thing, then you have an amplifier. Like that'll just amplify whatever you put in. Or this is also how a radio signal is also going to be a small voltage thing that could feed into a transistor. And then you could feed a big battery in here or something, and then feed this into a speaker. Right, so that's basically a transistor radio, or how a microphone and amplifier work in short, right? So it's basically, you can do it all with solid state. Originally, this stuff was all done with tubes. And then like, basically this was a much simpler, lower power way to do it. Right, so that's kind of the basis, this kind of switching, and then it's the basis of all the electronics, right? Solid state electronics, but the subcomponent is a PN junction, which is just basically a solar cell. That will just be a solar cell. If you use silicon, it can absorb in the solar spectrum. So yeah, these, if you see these on a board, they're like 3, because the middle one is that low voltage thing, and the other 2, the outside 2 are the thing that the current runs through. So you have a control voltage in the middle that controls the flow through the other things. So anyway, that's all that stuff is. So I wanted to do today, I wanted to go through this little thing, this stuff, the Gritzel cell thing. So let me hide this. This is the same plot, but like older, I think. There's probably a new one of this Enroll thing. Enroll's a lab in Colorado where they do, it's a Department of Energy lab for basically photovoltaics and it's a renewable energy lab. And so anyway, the Gretzels are the yellow, I think here, right? Perovskite cells, dye-sensitized cells. Those two are kind of in the same grouping. I mean, a perovskite cell is a dye-synthesized cell using a perovskite as a pigment. So the yellow is shooting up in the open circles here, and it flattens out. Right. So the perovskite. So once they found a better pigment, so that's the percentage here is like 9%, and I think the maximum percentage you can get from a silicon PN junction is something like 26. So somewhere in here. So that's the best you could ever possibly get from a silicon, like a commercial. Which is, it turns out, like, if you can make them cheap enough, it doesn't matter, right? But currently, China decided that they were going to make all the solar cells in the world. They've also decided they're going to make all the electric cars in the world. And their government decided it. So they dumped a load of money. So there were a lot of different, like, startup technologies for photovoltaics, like the cadmium sheets that go on your roof were being made in Toledo. That company went bankrupt. Like, a lot of the solar panel companies in the US went bankrupt because China just decided that they'd take the conventional like amorphous or polycrystalline silicon solar cells, PN junction cells, and just mass produce them for nothing. No. So they did that. So basically the price of solar cells went to nothing. So right now is cheaper, like much cheaper, like half as much to produce electricity with solar cells than any other technology. Like, I think the highest is coal right now, and the next highest is nuclear. Then gas is somewhat is like below that, and like 3 or 4 times lower is solar. It's basically because the Chinese are making so many of these panels, they're just churning them out. So there's not. I mean, now there's some made in Germany and then China, and they're a little bit competitive, but basically, it doesn't matter what percent conversion you have if you can make it cheap enough. I mean, if you can make it, if it's so that it's free, 26% or 100%, just put in 4 times more. If it's free, it doesn't matter. I mean, you run out of roof space at some point, but basically, we're not anywhere near running out of roof space in the US, because we have 1% in Ohio, 1% of the roofs are, or they could have solar on them, have solar on them. So we have, like, we're not out of roof space. It's basically, you could put this on every building. I mean, and everyone would be saving money. So the reason we're not doing it, it's hard to tell why, it's kind of crazy. So anyway, but this has a potential to, like, outrun this. There's no 26% limit to perovskite. This thing can go to 100%. There's no limit to it. So basically, even though this is like lower than the blue ones, it has a potential to overcome them. And also, people have done like economic analysis. I don't have this, but it's probably a web page that does this. But basically, you have to figure, if you dig up sand, right, and then you have to reduce it somehow, usually with high temperature and carbon, or with magnesium that you got through some carbon reduction process. So it's going to go into thousands of degrees. Then you get silicon. Then you have to take that silicon. It's not pure silicon. It has to go through. You have to put it into a chemical solution, right, with acids, and then it has to be precipitated out, and chemical reactions have to happen. So the whole process is really dirty, and it's really expensive to end up with pure, absolutely pure silicon you can make a PN junction with. So it's basically that if you figure out all the energy that you took to put into that. So the only reason that this exists because Chinese subsidies, and also because a lot of the solar panels are like secondhand from the semiconductor business. If you're already making a lot of silicon for computers and for electronics, and there's a lot of waste in that, because for those it has to be absolutely pure, like absolutely the perfect 111 crystal face. You have no pure impurity at all, otherwise the computer just burns, right? So it's basically, I think it's something like 60 or 70% of the silicon that they make for computers is just thrown away, right? So you can take all that, that's free, and then you can make solar panels. So if you figure out like an economic analysis on it, there's no way that you would do this, right? So you're looking for something that would be like a simple chemical process where you could just spin coat something like a thin layer and then have it be a solar cell, which is possible. Okay, so anyway, this guy, and it was originally done in Switzerland, in Lausanne, so like kind of near Geneva. It was a university. This guy Gretzel, he's probably retired now. I think this might be a little bit old. Anyway, actually, I didn't look at these before class. I didn't realize there was a Gretzel thing here. What did that do? Something that said something. I identified enable all hyperlinks in this file for this session. Do you want to continue? Cannot open. Oh, interesting. Actually, I didn't try these. So I don't know if they open. This says for all. And yes.
You might put also when you like click it, just copy, then highlight the link and copy it.
Yeah.
Like, we love-
Mm. It thinks it's a file. Yeah, I want to do this for some other things. I'm going to try it for this. See what I can do. Wait. No, that's not the right thing. I just copied it, I think. I'm gonna have to do this for some others, so. Oops. Let's see, copy link. That should work, right? Go here. Open up one of these things. That's not the right link. Maybe that's not a good link. How come it won't let me edit the link? Open link.
Can you copy from there, like where it has? the
Oh,
link?
yeah, thanks, good. That's perfect. All right. Haven't looked, thanks. Oh yeah, that's Gretzel. So he was a Swiss guy.
For us to develop these dye-sensitized cells. The dye-sensitized solar cell is the only solar cell that mimics the charge separation process in photosynthesis. It uses, like in the green leaf, it uses a molecule that excited by sunlight and generates electric charges.
Well, it's not that.
But the molecule is not involved in the charge conduction. So the charge transport and the photo-induced charge separation are separated. And that's not the case for all the other solar cells that are based on p-n junction
Yes,
semiconductors.
there.
The
Blah, 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 blah. That's it.
so we get very excited.
Anyway, that's who he is. Pretty good. Anyway, so the idea, I guess, maybe the original idea is so you have green leaves, there's these porphyrin rings. So like hemoglobin is the same thing. It's got iron in the middle, and it's got a porphyrin ring. So there's a lot of biological, this is like a crown molecule. It traps a metal atom in it. So that magnesium can kind of absorb sunlight and generate electrons, and we can kind of conduct down this thing. And in chlorophyll, that leads to like some kind of chemical reaction that happens. So it's like a pigment that can absorb sunlight, right? And it transforms it to an electron. So it's similar to the p-n junction, like absorbing sunlight, making an electron. So people thought about doing this, you know. So they were like in the 1968. So people were thinking about this idea, and they achieved it somewhat, you know. But what Gretzel did, I guess, is that so they used different. First, they actually used chlorophyll itself, right, and then so these were kind of biologists, and then they're kind of biologists that were also doing like they were just biologists doing this stuff, you know. So in silicon you have a semiconductor that's going to kind of go into the conduction band and then conduct the electron away once you generate it at the p-n junction. So they're going to generate an electron at an organic molecule, and then that electron is going to go into a separate. So silicon both generates it at p-n but also conducts it. So they're going to separate the conduction from the generation. So have a pigment that would absorb the light and transfer it to some kind of a semiconductor material that could transform it and then make that go to an electrode and then make a solar cell that way. Right. So it kind of seems to make sense. And we already have leaves, so you could use chlorophyll to do it. The chlorophyll has a pretty limited lifetime, for one thing. And it's like anyway, there were problems with chlorophyll. It wasn't efficient enough to really do this very well. So they tried doing it with chlorophyll, and then basically Gretzel decided to set up this cell where he used berry juice that had like black berry juice originally, and he took titania, which is easy to make. So titania is basically kind of sand is made of silica and titania, TiO2, and then you can make it also from chemicals. You can get TiCl4. You take titanium mineral, and dissolve it in like HCl, and you can break it up and make TiCl4. And the TiCl4 you can just burn. And you can make this white powder, and that's a pretty big industry. Like Chemours does that. And Degussa, which is called something else now. Chemours, and then Degussa is now something else. But anyway, there's two big companies that make titanium powder, and that's used for like white paint, like all the walls are made of that. That's why Tony said like, oh, white paint's going to be a photo cell, because it's the same stuff. It's the same things in white paint. So you just have to put berry juice on it and kind of make it into a layered structure and put electrodes on it, and then you have a solar cell. So that's basically the idea. The problem is berry juice also has a limited lifetime, and it isn't optimal for absorbing sunlight, right? So that's kind of the idea. So people, you have a network where you want to have conduct the electrons away to the electrode. So that's pretty much the scheme of a Gretzel cell. So Gretzel later found these ruthenium dyes were optimal for this. They were perfect match for the solar spectrum, right? So it's the same kind of cage compound as in chlorophyll, but ruthenium, which is a rare earth. It's one of these things that they mine in the Democratic Republic of the Congo, like little kids are mining it, right? So it's got some problems, but basically the biggest problem is it's really expensive. Like a little bottle of this ruthenium dye is like $1,000. Right, so it's kind of too expensive to use. But so there's other things you could use for this. But basically, the best, like when you look at that original chart, then like that plateau is ruthenium dyes. That's like it's the EPFL Zusan, what is it? Polytechnique something Lusan. So that's like the ETH of Lusan, the Swiss. It's in French. Whatever ETH is, École Technique Haute. And EPFL is French for the same thing. So they have like two big technical schools in Switzerland. Anyway, so this flat part is where they use the ruthenium dyes. And they got some improvement, right? So, and then after that, people just figured out like to use perovskite for the dye, and that had a huge impact. Like that. All right, it's stable. So this is kind of the idea. Like you have an anode, cathode. So here you use indium tin oxide or some other clear conductive material. And then this is titanium, white paint. You have an ion conductor, so it can carry the positive holes from the titanium back over to the cathode. And then you have the electrons kind of flowing up to the anode through the titanium. So basically, I have some videos of making these things, but let's see. So I'll do this. Copy them, open them. This is the one. Pretty long link. See if that works. I mean, I just show how to do this. Doesn't look like a YouTube link even. Well, yeah, it's pretty crazy. The guy's pretty famous. Like he got really famous after this, and there were companies that started making even with the ruthenium dye. So you get like because it's flexible. Like you can put paint on anything. You put it on plastic, so you can have like a totally flexible solar cell.
Yeah.
The other ones all have to be on glass because they have a silicon wafer that's like if you pick it up, it shatters. So you have to kind of glue it onto something stable like glass, and then like then you're gonna have a big chunk of glass you're hauling around with it, so you can't put it on a backpack exactly. You can put a small one in a like a calculator or something, but a big one that's gonna be enough to power a computer, it's gotta be flexible. You can't do it with the glass. So, and then people have gotten around by CVD depositing like cadmium stuff or silicon. That's flexible. You put it on like aluminum foil or something like that. But anyway, this is really actually flexible. You can do it on plastic. So basically you can do anything with it. Anyway, so they just show like, that's, that's you can do it. Like we did this, it seems like we did this in a lab. Yeah, I'm pretty sure. I remember at some point it was being done in a lab. It's easy to do. Like there's links on how to do it, you know.
Maybe we should do
Yeah, yeah, it's not hard to do. I think I might have some of these materials like in my research lab somewhere that that floating around, but it's not. There's a lot of people that show how to do it. Let's see. So it's that business, and then so ruthenium, blah blah blah, and then these are just graphics of the same thing, right? There's a lot of people that make a big deal out of it. It's pretty simple to do though. So this company though, right, so the perovskite one is a little bit different because you start with, I don't know if I have a picture of the chemistry of it. Basically you start with a precursor. So perovskite is on the Earth, it's the most popular crystal, but there's almost none of it on the surface of the Earth. It's all in the middle of the Earth because it only will form like at really high pressure and high temperature normally. But you can make it, and so perovskite's like a framework. It's got like 3 components. So it's got kind of a cubic crystal. And then within that cubic crystal, there's oxygen kind of in the middle faces. And then in the center is like a metal atom. In this case, it's lead. Okay, so the lead, and then the outside atoms are ammonium. So it's like ammonium cubic cage of a lead atom in the middle, and there's oxygens at the faces of it. So it's anyway, that crystal structure forms at the center of the Earth. And it's like most of the Earth is made of that crystal structure, believe it or not, but none of it is at the surface of it. So this stuff, you can synthesize that same crystal structure synthetically, and if you capture the right metal atom in the middle, it can absorb like sunlight exactly at the frequency of the spectrum of the solar spectrum. Then it's a perfect dye. And it's also a stable crystal. They can make big crystals of it, like purple crystals. So anyway, so the original thing was just use that as a dye, replace it with ruthenium, and this is lead. It's really cheap, and you can do it. You can make this dye. So the ruthenium dye you had to make in a special kind of bio lab. It's almost like making chlorophyll or something. This dye you can make anywhere. You just need kind of a hot plate to heat it to make the crystal form from the precursor salts, and then the crystal just grows out of it, like kind of magically. So it's like, it's pretty impressive to do a demo of this thing. Let's see, this thing, I think they show how they've progressed. what's wrong with this picture? I got this thing. How do I get the, oh, I don't want to update now. I want to enable editing. How do I get rid of update now? Here. All right, this thing could be what I want. Edit mode. Use that. All right. Maybe this isn't the one I want. One of them shows a video of all the processes, how they've improved the process from the original. So Gretzel also invented this perovskite pigment. So Gretzel invented the berry juice. Then he invented the ruthenium, and then he also came up with this perovskite. But once they got perovskite, like everyone jumped on board. In between, like when there was just ruthenium, there were companies making like solar cells for backpacks and things, but they all went out of business. Like it turned out like it didn't last long enough. There was some kind of commercialization problems. Once they got to the perovskite thing, then like everyone's on board. I mean, including like Tony. Right? So everyone's like talking about it because it's like the stuff is stable. The problem is like what leaches out of it when you put it on someone's roof is lead. Yeah, so the lead, the pigment thing that you're using is toxic, and it hurts little kids, right? It's lead paint. So basically, you're talking about paint. Yeah, you can do a white paint, but it's a lead paint. You know, it's like we got rid of lead paint a while ago. So
Is there a way to prevent the lead to come out of it, or is it just?
yeah, I mean, there's companies doing this now, so it's not just like academic. You know, so I think these companies are have everything figured out pretty much.
Oh gosh.
And then at that point, it becomes politics kind of, because you have basically China. You know, in China, the last thing they want is so how did I get this? I did copy.
They didn't fully let delete your own link.
Oh,
When you went to the
okay. Let me try this again. I'm gonna get rid of that. All right. All right. Yeah, you're right. Thanks. All right. So these guys, somewhere they have like their whole vision of what they've done. You know, material solar cells, equipment, news about us. I think it's like about us. There's a video somewhere in here. I watched it last night. It was pretty good because they showed how they went through the sequence of the technology. There's a lot of links here. Fortunately, I didn't pick the right one. Innovations Australia. Improvements. Perovskite solar cell for definitely perovskite improvements. That sounds like the right thing, but it's made on the map. This is a video.
It's time to improve your writing game with Grammarly Go.
Yeah, this is it. So they show the perovskite crystal structure, which I tried to describe. So the green things are ammonia, and then the middle is lead, and then there's oxygen are the red things. And then you can grow these crystals, and then they show this thing. Let's see. One of these shows like how they've improved it. So it isn't the Gretzel cell anymore. They've turned it into like layered structures. So there's no, like there's a liquid. The Gretzel cell uses liquid iodine solution for the electrolyte. And like there's no electrolyte anymore. They use like a polymer electrolyte.
A general process, methylammonium iodide,
I found out that like adding DMF, when you form the perovskite crystal, if you add DMF, which is a toxic solvent, like it's kind of nasty, it dissolves screwdriving sometimes. So anyway, DMF isn't a great thing, but basically when you add in DMF to these salts and you're forming the perovskite crystal, somehow it makes it so there's no defects on it. So you can make like big crystals, you know. So it's basically the DMF, they patented that. They patented like every little twist on this thing. And in the end, like they have this so that this is like a real commercial process, you know. Anyway, we could listen to this whole thing. I listened to it last night, but it's pretty not bad. case, there's all these predictions like perovskite, this kind of Gretzel cell perovskite thing is just gonna be everywhere. And it should be, like if it was a fair playing field, we'd already have this.
In 2020, photovoltaic energy is expected to be the most promising part of energy industry thanks to its competitive cost of production. There is a precondition for its realization, however, development of a new technology that overcomes limitations of conventional solar cells. In that sense, the solid-state perovskite solar cell first developed by Professor Park's team is the most winning alternative. Perovskite consists of two cations combined with three anions, a three-dimensional crystal structure. The central cation is metal like lead, and a cation at each vertex is organic material like methylammonium. Halogen elements like iodine are located as anions in the middle of the vertices. As perovskite features an outstanding absorption coefficient, it can replace organic dyes of conventional dye-sensitized solar cell. However, we have an issue here. Liquid electrolyte inside the cell dissolves perovskite, compromising stability. Professor Park's team solved this by adopting a new technology with a solid pole transporting material instead of liquid electrolyte. In terms of the power conversion efficiency of a perovskite solar cell that uses a solid hole transporting material, it was merely 9.7% in the initial stage of development, but dramatically improved to 20.4% in a matter of 3 years. It still keeps rising.
Eventually,
Costing only 1/10 of silicon solar cell, realizing equivalent efficiency is possible since its raw material is cheap and manufacturing process is quite simple.
yeah,
Its figurative structure was identical with DSSC in the beginning and later developed into meso-super mesoscopic and planar structures. Accordingly, it was possible to substantially reduce its thickness.
this already was.
This is because perovskite, unlike dyes, demonstrates much higher absorption property along with excellent charge transportation. The perovskite solar cell has not only exceptional durability, but outstanding flexibility. Its three-dimensional crystal structure is fully restored to the original state in the course of being bent and unfolded. Being thin, light, and flexible is a great advantage.
Yeah, I mean, they're actually like blocks, they don't flex, you know. It's a crystal.
For a high-efficiency solar cell, high-quality perovskite is requisite. In a general process, methylammonium iodide and PbI2 are dissolved in DMF for spin coating.
It just grows out. Like it's,
A problem at this point is that the solvent evaporates too fast, generating small and non-uniform perovskite crystals.
yeah, just grow.
The research team developed a technology to manufacture high-quality crystal using a duct. When dissolving methylammonium iodide and PbI2 in DMF solvent, DMSO was added in the course of spin coating so that the evaporated solvent does not form crystals. This is what we call adduct. Such adduct turns into quality perovskite during heat treatment and DMSO disappears and crystal growth rate is controlled.
Never could perovskite crystal. It turns out like the most crystals are perovskite. Yeah. But this
Grains can be observed when the surface of perovskite is enlarged. The groove between the grains hinders electrical properties.
that is.
The research team developed a non-stoichiometric adduct technology to maximize electrical efficiency of perovskite. It was identified that if adduct is made by adding a slightly excess methylammonium iodide in the course of making a solution, the unreacted methylammonium iodide left after crystallization sticks to the grain groove, improving electrical characteristics. In such a case, the affected area even serves as a pathway for electrical conduction. This technology is innovative as it enables fast manufacturing of high-efficiency solar cells through the low-temperature solution process using inexpensive raw materials. Its distinctive feature maximizes efficiency of perovskite. It has a wide range of applications, such as alternative materials of conventional photovoltaic system, electric car charging, and materials for silicon tandem solar cells, etc.
The thing is, I had a car.
It enables large area coating and can be used for a wide range of applications thanks to its thinness, lightness, and flexibility. The durability of this technology was proven by demonstrating stable efficiency even at 85 degrees Celsius as well, heralding a new innovation in the solar cell industry. This technology has been reported to the academia through as many as 42 papers. In the case of a paper published in Scientific Reports in 2012, its academic value has been highly recognized by being cited more than 2,400 times. Regarding industrial property rights, 19 domestic patents and 5 overseas patents have been applied for, and 6 out of them were registered. This technology has been fully developed and now is in the phase of technology transfer.
Looks like you need that whole. It's not enough to, it's in the, it's like 200 watts, right? It's like 300 watts.
Hi, my name is René Williams. I'm assistant professor at the Molecular Photonics group at the University of Amsterdam.
Anyway,
And today we will
so
discuss.
there's tons of stuff if you look for perovskite about solar panels. I mean, it's just TED Talks and everything, but
How much there is about it. And I've
Yeah.
never heard of it before.
yeah, there's a ton of stuff. Like the thing is, it's not that much. It's at commercial stage at this point, so this isn't that much academic research has kind of dwindled down. And plus, like the NSF and the DOE, they aren't really funding academic research in solar panels anymore because I think they think it's reached the state where it's commercialized. So, yeah, it's kind of funny. Like there could be a lot of windows of opportunity that are overlooked in a sense. But anyway, so that's about. I wanted to mention. Someone asked about perovskite, or Tony mentioned it, so I thought I'd say what it was, and maybe why we're not using it. I mean, we will eventually use it because it's cheaper, and it makes a lot of sense to do that versus like you burn in a lot of carbon to make the solar panels. Ton of it because it's got to go to a really high temperature and that has to come, and also you're trying to reduce oxides, so that's going to take coal, so you can't do it without coke. So the coke is processed coal, so like it doesn't make sense if every solar panel you make is releasing so much CO2 because it's not going to work out. So but this thing doesn't release any CO2. I mean, there's simple chemicals like amines and stuff, the things that are just in the chemical industry already. So it's not much. The only problem is the lead. But basically, if you seal it good enough, maybe that's okay. The idea of painting your wall with lead isn't really going to go anywhere, I don't think. But if you could seal it with something that would last forever, maybe you could do that, I guess. But
I went to a conference during my co-op with Duke, and we just they talked about with the switch to all EV electric vehicles.
Yeah.
How the grid not ready for that switch, all of that. Do you think that the solar panels could kind of help alleviate?
I mean, in the 1960s, people went from drying their clothes outside to drying their clothes in a dryer. The dryer uses the same electricity as an electric car when it's charging. It's exactly the same.
Yeah.
It's no one ever talked about the grid blowing up. when
Yeah.
people went to electric dryers. Or you could stop using your electric dryer, you know? I mean, so
Yeah.
I think that in a lot of ways, there's something to it, but really it's a pretty minor, I don't believe what they're saying about that.
Yeah.
Because we've gone through a lot of transitions in boosting our energy use. And the power companies only seem more than happy to provide it, you know? Like all of a sudden they have a problem with it, you know? So I don't, and also, I mean, I have some slides on the grid and stuff. So there's a big advantage that you can port the storage capacity to work. I mean, if people are still going to work with a new kind of working environment. I mean, a lot of people are Zoom working, you know, even after COVID, but anyway, if you're driving and you're taking around like the Tesla's, there's 100 kilowatt hour battery in it. It's a huge battery, you know, so you can port that and the energy in it. I mean, it weighs the same if it's charged or not charged.
Yeah.
So you drive to work and you can need the power to run air conditioners downtown, just plug them in there. And then like pay back something if you're drawn out of it. I mean, so basically the power becomes a lot more portable when you have electric cars. So it's all in a lot of the business of the grid. So you have a peak and down, like if you map out the energy usage, you know, and then like downtown is a big peak during the day and then it drops down and the suburbs come up. So they have to, the generation capacity of the power plant has to match that peak at that location, right? So and they have to build the plant to be able to do that. And then the rest of the time, the plant's not running at full capacity. Like maybe it's running at 50%. So they're already throwing away a huge amount of power. If you could take the batteries from the cars that charge somewhere else, take that power there, or use that to suck up the power. So you have this mobility thing with electric cars. So all you need is wiring. You know, the wiring is the big issue. It isn't necessarily like, can you do it?
Yeah.
You know, it could make things even a lot better. Like we could get by with half the power plants that we have if you have the right kind of grid for the thing, right? So a lot of it is just wasted. So I don't know. I mean, it's going to take some people thinking about it and some infrastructure stuff, but it's not the end of the world. And plus, like if you drive an electric car, you would never drive a gas car again because they're much better.
Test drove the hybrid, like the Honda Accord, but it has
Uh-huh.
the Genesis battery, so it's not.
Yeah,
plug-in.
those stink. Those are no good.
Yeah, that's what, well, it was so.
I mean, I had like 5 Priuses, you know,
Mhm.
they just slow, and that's the problem. They're like really slow. The new Prius is kind of faster, but basically it's nowhere near. An electric car is like driving a rocket ship.
Yeah.
It's just like it's dangerous. I mean, you can go like 0 to 60 with a Chevy Bolt. You can go, which costs like you can get the bottom line one for 20 grand with a tax write-off.
Yeah.
You go from 0 to 60 in like 5 seconds. Yeah, it's dangerous. It's a dangerous car, you know. And like once you drive that and you go into like a Honda Accord, you're like, what is this? You know, it's just like nothing. There's no comparison, you know. So nobody's going to drive a gas car once they drive that, you know. That's what I think. So it's not going to be like environment that's driving it. It's going to be people just don't want to drive a slow car, you know, that pollutes too, and you have to pump gas. Like around town, you never go to a gas station. You just once in a while you plug it in at home. I mean, it's pretty easy. It's actually so much less time involved. And in worrying about, am I going to run out of gas or something, you know, so you don't, yeah, it's a lot easier around town. For long trips, it's kind of a little bit dicey because there's no infrastructure for charging on long trips. There's enough to get by, but just barely enough. With Tesla, it's different though. Tesla, like before they sold the cars, they built all these charging stations, and their charging stations are something like, they're like 500 kilowatt charging stations. Like the Bolt charges at 50. So they're 10 times faster, you know, so they're like incredible. And they built them like everywhere and it's mapped out, and the car has a computer in it that tells you where to go. Yeah, so I mean, the Tesla's the way to go, I think, in a lot of ways, if for trips, you know. So with that, it's not different than a gas car in terms of convenience, you know. With the Bolt, like all the other off brands, like the long trip isn't kind of a nightmare, you know, because there's not enough. You have to really figure out ahead of time, like where you're going to charge it from. But around town, like, there's no comparison at all. And like, most of the driving you do is just like around town, yeah. So I mean, and their efficiency is so much higher, you know, they're like 98% efficient. The gas car is like 20%. It's like, yeah, if you think about the barrel of oil, to refine it takes something like 40% of the energy value to refine it. And then to transport it takes 10% or something, and then burn it in a 20% conversion car. So you've thrown away like 90% of the energy value of the oil you started with. It's just tossed, you know, before you even burn it and make carbon in the car and dose yourself with carcinogens. You know what I mean? So it's like, it doesn't make any sense. Like anybody, if someone invented that now and you had electric cars, they'd be like, you must be crazy. Like, who would buy this thing? You know? So I think that once a couple people buy them, you know, no one's going to buy a gas car again. The transition will happen like overnight, I think. And the grid will just catch up. I mean, I'm not really worried about that. If there's money to be made, you know, they will definitely do it. And so, because even if you burn coal to make the electricity, so the coal, because it's like high temperature, so it's like 70% efficient or something to burn coal. So even that's more efficient than making gasoline and oil. Like, it's much more efficient. So, and then with the 98% efficiency of the car, like, you're still way ahead. Even with burning coal, you're still making less CO2. I think it's something like a factor of 4 or 5, even if you use coal to power the electric cars. So I don't know. To me, like, people just need to drive one. Yeah, the hybrids almost are like, they're bad because they make you think like this thing's going to be like a lower performance. And actually the performance is way better. Like, there's no comparison at all from the performance end of it. So, I mean, I think you're worried about burning tires out because there's so much torque. Like, it gets you in a mode of like race car driving or something. Yeah, so you spend a lot of money on tires, but it never needs any maintenance at all. Like, there's no maintenance for it. The maintenance schedule when you buy a new electric car is rotate the tires.
Yeah.
That's it. That's all you do for the life of the car. It's like, so.
I heard something about like the battery too. If you have to replace, like, the battery can go bad. At least when I was looking at the hybrid, like there's a 10-year warranty on the battery.
Yeah.
So you could replace 6, 7, 8 grand, which is pretty bad.
Yeah, I don't know. They talk about that, you know. I know a few people that have electric cars and no one's ever had any problem with the battery at all, you know. And I've owned 5 Priuses, you know, all of them have over 150,000 miles on them. And the battery's the same as when they were new, as far as I can tell. I mean, they get the same mileage. I mean, they're getting like 50, 60 miles a gallon. So it's pretty good, but you're still burning gas. You still have to, once in a while. I mean, with the Prius, you can drive 600 miles on a tank, you know, and the tank's really small. It's like $20 or whatever, $30, I don't know. But so it's pretty good, but you know, slow. Like, the car is slow, and it's slow pickup, it's slow everything. So you have to kind of get used to it. It's safer, you know, because you're driving slower. The electric is much more dangerous, you know, because you can just at a stoplight, you can blow everyone away, and it doesn't make any noise. Like, it isn't like you're in a race car and it's making all this noise. You just push on the gas and like, you'll notice like every other car's in your rearview mirror and you don't even notice it, you know, because the car made no noise at all. So it's pretty weird. I mean, I'd imagine that like once people drive those, you know, they're not going to go back. I mean, no one's going to go back. And then all the gas cars are going to be like dinosaurs, you know. So, I mean, it's pretty weird, but basically I don't see that the transition is going to be short. It's just going to be boom, like, especially like the government incentives and everything, you know. So it helps, but even without those, like, the technology has reached the point where it's just, there's no comparison, you know, between the two modes. But I'm surprised, like these Amazon trucks and post office and everything, like, I don't know why they aren't all electric. And the school buses, like, why aren't they all electric now? It's stupid. It'd be much cheaper to run the things, you know? I mean, I don't know, like, put all the kids in this thing. All right, school buses, like the back seat of the school bus is the highest dose of nanoparticles of any kind of occupational thing, because the diesel exhaust is full of like carbon nanoparticles. Yeah, and it just doses the kids in the back seat. Plus, you're sitting on top of this gigantic tank of diesel,
Yeah.
and the other chemical fumes coming out of it. So why not? I don't know why they wouldn't just have those all electric, you know?
Yeah.
It doesn't, that's really crazy. Like, it's not safe, really. I mean, they talk about safety of electric batteries or something, but man, you're really sitting on a bomb when you got a tank of gasoline. You know, it's really seriously a bomb. And you see people, like, there's a sign at the gas station that says, "Don't use your cell phone." And people like pop out their cell phone. It's because the fumes will ignite, like any spark, and the whole place goes. Everyone there is dead. Like, why would you open your cell phone up there? It's like they don't understand, like, the flammability limit of the fumes from gas. You're right at it when you're pumping your gas, you know? So any spark, like if your phones have lit it off before, you know? So it's like, that's why there's a sign there that people still use them. I mean, so I don't know. That always gets me. It's like, oh, pull out your cell phone, you're pumping the gas, you know, think about what you're doing. But anyway, plus the breathing those fumes is bad, you know. I think if it was if you were at a company, they would never let you do that. Right? You'd have to have PPE or something. But so anyway, who knows? Not that I'm biased, you know. So it's my 2 bits on it. If we go to the power plant, you can ride in my car if you want.